Good morning, viewers. Today's class is a continuation of our first video class on axis of symmetry. Today, I plan to discuss planes and center of symmetry. A plane of symmetry is an imaginary plane bisecting the molecule into two halves such that each half looks like the mirror image of the other half. To get the mirror image appearance, one has to carry out a movement or operation called reflection. You can think of this dividing mirror plane as an extremely thin plane having reflecting surfaces on either side. It is very much unlike ordinary mirror where it reflects only from one side. Students of stereochemistry are familiar with taking mirror image and trying to superimpose the mirror image with the original configuration in testing for chirality. Our symmetry plane is not at all like that. It has to pass through the molecule, bisecting it, such that the two halves look like they are mirror images of each other. Let us illustrate it with the planes of symmetry for ammonia molecule. We have been drawing ammonia molecule as a projection with its threefold axis of symmetry perpendicular to the plane of drawing. The hydrogen atoms are numbered 1, 2 and 3. We are just labeling it for distinguishing among the hydrogen atoms. A plane containing nitrogen and one of the hydrogen atoms. A plane like this, or a plane like this, or a plane like this. All these are planes of symmetry. We may draw it as the symbol for plane of symmetry is sigma. This contains hydrogen 3 and nitrogen. This contains hydrogen 1 and nitrogen. I will put it as sigma dash. And this contains hydrogen 2 and nitrogen, sigma 2 dash. Here, the nitrogen and H3 are in the plane sigma. When reflection is done, atoms in the plane do not get shifted to any new position because centers of these atoms fully lie in that plane. But atoms outside the plane get reflected. How exactly one does the reflection operation? From every atom outside the plane, you draw a line perpendicular to that plane, extend the line an equal distance in the opposite direction and put the atom at the new terminus. So this hydrogen becomes H1 here and this H2 on similar shifting will change to hydrogen 2 here. I'll write the look of the molecule after the reflection operation is done as a separate figure. H3 is not shifted, H2 comes here, H1 comes here. This is the original appearance 1. This is the appearance of molecule after reflection. 1 and 2 are alike. Without the labels, you cannot distinguish them, but they are not identical. With the labels, they are distinguishable, but labels are put by us. For testing symmetry, it is enough that after an operation, the molecule develops into an equivalent appearance. But if I repeat the operation of reflection for a second time, then it is very clear that this H1 will come here and H2 will go there and you will get back appearance 1. So if I put one more sigma, sigma followed by sigma, you can write it as sigma squared, will bring the molecule back to its original look with all the labels, they are exactly like appearance 1, as if we have not disturbed it at all. The act of doing the thing is indicated by identity. So I can write sigma squared is identity. What happens if one more sigma is done? You get appearance 2. And again one more sigma 4 times, it will be original appearance 1. Therefore, we can write an equation. Sigma to the power n is equal to sigma if n is odd, or equal to identity if n is even. So apart from identity, the plane of symmetry generates only one distinct operation, which is sigma itself. By the by, the notation for elements of symmetry and operations associated with it is the same. Earlier, we have used n-fold axis of symmetry as Cn, but suppose I say a Cn is done on the molecule. The same Cn tells you that it is rotating the molecule by an angle of 360 divided by n degree. Likewise, sigma is a plane of symmetry, it's an imaginary planing bisecting the molecule. But if sigma is done, means the molecule is reflected about that plane. So for the reflection operation and the plane, the same notation sigma is employed. Let us analyze water molecule for planes of symmetry. Coming back to ammonia, in addition to sigma, it has sigma dash, which contains nitrogen and H1 in it. These 3 and 2 gets mutually shifted, and there is sigma 2 dash, where hydrogen 2 and nitrogen remain in that plane, and hydrogen 1 and 3 get mutually interchanged by the reflection operation. Let us do it for water molecule. I am rubbing this off. Water is a bent molecule with 2 hydrogens and labeling them as 1 and 2, and this is its principal axis. That's only one axis, C2 axis. Now such a plane bisecting the hydrogen-oxygen-hydrogen bond angle will be a plane of symmetry, because only oxygen lies in it. H1 and H2 get reflected in this way. This H1, draw a line perpendicular to it, extend it in equal distance, put the H1 on the right side. Similarly, H2 gets shifted to left side. So after this reflecting plane of symmetry, which is sigma, we get the appearance of molecule as H2 here, H1 here. This is appearance 2 and this is appearance 1. With the labels they are different, but without labels 2 is indistinguishable from 1. And if you repeat sigma for a second time, again you get appearance 1, as if you have not disturbed it at all. Or sigma squared is identity, sigma 3 is sigma, etc. Now, water is a planar molecule as well. The very plane of the board where I have drawn it, all the atoms completely flatly lies in it, and this is a plane of symmetry for water, the very molecular plane itself. If the molecule is reflected in its molecular plane, it is very evident that none of these atoms, their centers, will not be shifted at all. So I will denote it as sigma dash. So sigma dash will give H, O, H. Even with the labels, there is no difference, appearance 2. Now a natural doubt can come. Are 1 and this 2 exactly identical? Or if I say If a sigma dash is done, are you getting a result as if you have not disturbed the molecule at all? The question can come. But on second thoughts, it is very clear that it is not like that. Although the atoms are extremely tiny spherical entities, on a reflection, the centers are not shifted, but the facing side of the spherical atom will be going back, and the rear side of the atom will be coming to the front. Suppose I draw the atoms as tiny spheres in this manner. This is hydrogen 1, this is hydrogen 2. If the front side is denoted by a tiny into mark for all the atoms, oxygen as well as hydrogens. When the sigma dash is done, what happens? When the sigma dash is done, this front side will go to the back and the rear side, which was not marked, will come to the front. You will get H1 and H2. You can see that this appearance I have written here at the top is slightly different from this appearance, because here the marked side has gone back in the second figure. So only on repeating this sigma dash you will get the original appearance. Here the distinguishing marks for hydrogen atoms are twofold. We have distinguished them by 1 and 2, and also distinguished their front and the rear side with a into mark on the front side and no marks on the rear side. So take it from me that if a plane of symmetry is present, only even number of its repetitions will create identity. A single doing of sigma will only create the appearance created by sigma. Analyze molecules with many planes of symmetry. I have a model here of platinum tetrachloride, which is square planar. Tetrachloroplatinate 2. Here, this is a plane of symmetry. Actually, when you draw the molecule with its C4 axis at 90 degree to the plane of the board, like this, C4 axis at 90 degree to the plane of the board, the plane can only be denoted in this manner. Here is one, here is another one. This is another plane. Here is a plane of symmetry in this manner. Here is a plane of symmetry in this manner. So there is sigma, sigma dash, sigma 2 dash, and sigma 3 dash. The unmarked portions are the other end of these planes. These planes can be nicely understood from a plastic model which I borrowed from my parent department. Here is that. This is platinum tetrachloride, and here I have put, this is the C4 axis. I have drawn it in such a way that C4 axis is perpendicular to the plane. So I have to hold it in this manner. Hold it in this manner. So this is one plane, here is another plane, this is the third plane, this is the fourth plane. And the line of intersection of all these planes is coincident with the C4 axis. When two planes intersect, there is a line of intersection. And here, the line of intersection is the same as the C4 axis of platinum tetrachloride complex. And you can notice at the middle a red square, which is the square plane of the complex itself. Being a planar molecule, it has an additional plane of symmetry, the very molecular plane itself. That is denoted by this. So total planes of symmetry are 1, 2, 3, 4 and 5. And the fifth plane, if I hold the molecule with its principal axis as vertical, this fifth plane is horizontally aligned to this principal axis. We shall refer to this horizontal alignment, vertical alignment, etc. after a few minutes. Another example is that of benzene, similar style. Here is a plastic model of benzene, where if I draw the benzene as a hexagon, regular hexagon, the various planes are 1, 2, 3, 4, 5 and 6. These 6 planes are illustrated in this model. I will hold it in this manner so you can see the 1, 2, 3, 4, 5, 6 planes. As a projection, you can only draw lines. This is sigma, sigma dash, sigma 2 dash, sigma 3 dash, sigma 4 dash and sigma 5 dash. These are the other ends. When you are talking about other elements of symmetry, the same lines may be also be denoted C2, C2 dash, C2, 2 dash, etc. Planes of symmetry are of 4 types. Sigma is of 4 types. A plane of symmetry without any subscripts attached to it, a plane of symmetry with a subscript V attached to it, a plane of symmetry with a subscript H attached to it, and a plane of symmetry with a subscript D attached to it. This is simply plane of symmetry. This is called vertical plane of symmetry. This is called horizontal plane of symmetry. And this is called dihedral plane of symmetry. Simple plane of symmetry is possessed by molecules which have no other elements of symmetry than the plane of symmetry alone. They are planar molecules without any other element of symmetry. Of course, identity will be there. Think of a molecule like benzene having a substituent chlorine here and a fluorine here. 1 chloro, 2 fluoro, benzene. It is a planar molecule, and any planar molecule has the very molecular plane functioning as a plane of symmetry. Because it has no axis or any other symmetry elements contained in it, this plane is simply called sigma. Another example is HOCl, hypochlorous acid, or even HOD, monodeutylated water. All these are planar molecules but possess no other element of symmetry, and their plane is plane of symmetry. Then what is a vertical plane of symmetry? It is defined as plane which contains the principal axis. Conventionally, while discussing molecular symmetry, the molecule is held with its principal axis vertical. I am supposed to hold the model of platinum tetrachloride molecule in this manner. This is the principal axis which is vertical. This is the principal axis which is supposed to be vertical. So this line is present in all these 4 planes. These planes which contain the principal axis in it. Principal axis being vertical, these planes are called vertical planes of symmetry. And this plane marked by the red color, which is horizontal to my style of holding it, is called horizontal plane of symmetry. Platinum tetrachloride complex has got not only 4 vertical planes of symmetry, it also has horizontal plane of symmetry. What is horizontal plane of symmetry? I will say it is simply a plane of symmetry at 90 degree to the principal axis. There need not be vertical planes. For example, think of a molecule, planar molecule like BOH, OH, OH, H3BO3. It's a planar molecule, BOH, 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 and this is a C3 axis. This is a C3 axis. Here it is a C3 axis. Because it is a planar molecule and it is at 90 degree to the C3 axis. This is sigma H and this is C3. Then dihedral plane of symmetry. For beginners, you will simply avoid its explanation, saying that it is a special type of vertical plane of symmetry. The speciality being it will be bisecting a pair of horizontal C2 axes. Vertical plane of symmetry bisecting a pair of horizontal C2 axis. Horizontal C2 axis. For beginners of the topic of symmetry, we will just leave it like that. But the viewers, many of you are supposed to be familiar with this topic, may not be fully clear of certain concepts. So I'll explain the concept of dihedral plane of symmetry with the two examples. One example is the staggered conformation of ethane. Staggered conformation of ethane. In the study of conformations, you should be familiar with drawing the conformation in various projections. There are two popular projection formulae. One is the Sawhorse projection, another is Newman projection. In Sawhorse projection, the staggered conformation of ethane will be CH, H, H. You draw a long line, then put CH, H, H. The hydrogen atoms on either carbon are maximum away from each other. Now this conformation is not very useful in grasping the dihedral planes of symmetry, nor the location of the C2 axis. Of course, the C2 axis are three lines in this manner bisecting the carbon-carbon single bond. A better projection formula is due to Newman, where the front carbon is simply a dot and the projection of three hydrogens on the board. Although the sp3 HCH bond angle is 109 degree 28 minutes, when you project that in this manner on the board, the bond angle looks like 120 degree. This is the front carbon with the three hydrogens H1, H2 and H3. The rear carbon, back carbon, is denoted by a circle. And because it is staggered, the hydrogen atoms there, H4 and H5 and H6. The angle between the front carbon hydrogen bond and the rear carbon hydrogen bond, it is 60 degree. We call this angle as dihedral angle. Dihedral angle is defined as simply an angle between two planes. Here the plane, here is a plane, here is another plane. The angle is 60 degree. Now this molecule has a threefold axis of symmetry like this. It has a threefold, I am holding a line. It is an iron rod. I am holding it here as the threefold axis of symmetry. Apart from that, this is a plane of symmetry. And what does it contain? It contains a pair of hydrogen atoms, opposite hydrogen atoms, and the two carbon atoms. I shall illustrate this plane by creating another model here. Here I have this model of ethane. I have inserted into a planar board so that this plane of the paper, it is a plane of symmetry. You can see this hydrogen and the two carbons are in the plane. These two are projected to either side and these also. So this is the plane I am implying. The plane contains carbon atoms and a pair of hydrogen atoms, and such a plane is denoted here. Outside the plane we have C6, H6 and H5 and H1 and H2. If you do reflect it, what happens? Atoms in the plane remain there, but these two get exchanged. The rear hydrogen 6 and the rear hydrogen 5 get mutually exchanged, and the front hydrogen 1 and front hydrogen 2 mutually get reflected by drawing a line perpendicular to the plane, extending it an equal distance in the opposite direction and putting the atom at the new terminus. That is exactly how one carries out reflection operation. So if you have understood the concept of this plane, here is also another one. In order to make it a plane, I will just put it by means of slightly wider plane, and here is the third one. This is the plane of symmetry. These are the three planes of symmetry. Now, look at this dihedral angle in the Newman projection. There is no harm drawing a line bisecting this 60-degree angle. You can easily interpret this line. Actually, this line is passing through the middle of carbon-carbon single bond. You can interpret this line very easily in this projection as a twofold axis of symmetry. How is it interpreted? Suppose I rotate the hydrogen 6 and hydrogen 3 about this line. Along with the rotation of hydrogen 6 and hydrogen 3, carbon 1 and carbon 2 by 180-degree rotation will exchange positions. Here also it is actually 180-degree rotation. You can imagine something like a 60-degree funnel-like appearance where this is at the back of the funnel and this is at the front of the funnel. Where front of the funnel. This is at the back of the funnel. So the line at the front will go to the back and the line at the back will come to the front. So this type of a rotation. Along with this interchange, it is 180 degree. From this point to this point, it is 180 degree. Just like this funnel-shaped laying of these hydrogen atoms at the other end also, you can this type of H4, which is at the rear, will come to the front, and H2 at the front will go to the back. So if you have understood that this is a C2 axis, it is easy to interpret this as another C2 axis and this as another C2 axis. The same argument applies there. Here is C2, here is C2 dash, here is C2 2 dash. The other dotted lines are the other end of this same lines. So only one side need be marked. And look at how our vertical plane of symmetry now lies. The vertical plane of symmetry, this is vertical C3 axis and this is our plane of symmetry. And this plane and this plane are such that they are bisecting a pair of C2 axes. A pair of C2 axes which are lying at 90 degree to this direction. If this is vertical direction, that any line on the board is at 90 degree to it. So if you call this direction as vertical, these 90 degree dotted lines are described as horizontal. That's all. So a pair of horizontal lines are intersected by these planes. That is why the vertical planes get this speciality designation as dihedral planes. And one more interesting example can be described now. It is the case with allene. Allene is stereochemically a very important compound. CS2 double bond C double bond CS2, propadiene or allene. Here the terminal carbons are sp2 hybridized and the middle carbon is sp hybridized. And the more interesting thing is, if this CS2 group and the carbon lie in such a plane, this CS2 group and this carbon lie in another plane at 90 degree to it. Here also I have prepared a model to show you how allene looks. I hope you can see this. Here is a plane which contains CS2 double bond C, and here is another CS2 double bond C. The two planes are at 90 degree to each other, and look at the angle between these two planes. What is the dihedral angle at the middle carbon? Everybody can appreciate an angle like this at the middle carbon. This is the dihedral angle of 90 degree. And if you have a line bisecting that 90 degree dihedral angle, it will be a line oriented at a 45 degree. 45 degree is what you get on bisecting 90 degree. Here is one and here is another one. Here also, more than the real model, a projection of allene will give you a clearer idea of this C2 axis and the description of these planes. These planes are actually dihedral planes. Here is a plane that bisects the molecule. These atoms lying in the plane are not shifted, but these will be shifted. Hydrogen at the top will come down, hydrogen at the bottom will come up. So here is a plane of symmetry. Here is also a plane of symmetry. Let me draw or try to represent propadiene by a Newman projection like diagram. The front carbon, which is a dot, and the hydrogens attached to it are almost along a straight line. Middle carbon we shall draw later. The rear carbon, the carbon 3, it is at the back and the hydrogens attached to it are in this manner. So that you can clearly see the dihedral angle. This angle is very clear in the diagram. And where is our middle carbon? Middle carbon, let me introduce as a new circle here, a dotted line circle. This is the middle carbon. Now, bisecting this dihedral angle